Now let's look at how digital I/O in our Freedom board looks in detail. For this example, we're going to be using port D bit 5. This is a picture of our microcontroller. This is the chip on the little red board that is the core of the processor. It has 100 pins and they have a bunch of different types of functionalities, right? You'll see things like PTC6 is low level wake up pin 10. There's all kinds of interfaces that allow it to do different types of things. Like this is the real-time clock in. This is a USB interface. There's all kinds of different things that all of these pins do. So each pin has multiple functionalities. There's only so many interfaces to the outside world. There's only 100 pins. Maybe 10% of them are taken up with voltage and ground pins, communication interfaces, things like that that support the electrical functionality of the chip, and maybe 80 pins are left for general purpose I/O and communicating with the outside world and doing things, right? So the processor is very, very capable, and to be flexible for multiple different applications, it's set up so that you can configure each of these pins to do different things. You might have this GPIO pin controlled directly by software, so we can, from software, turn it on and turn it off. Or you might have it set up to be a PWM, which is a recurring signal that's automatically driven by a timer inside of the microcontroller. So when the timer goes off, it puts the pin low. When the timer goes off again, it puts the pin high, and it automatically generates a signal that way, right? That's a piece of hardware that's doing some work for us. So that's some context of how and why we need to do so many of these steps just to be able to turn a pin on and off on a microcontroller like this. I know some of you might have an aversion to Logisim, so we're not going to be using it to design things in this class, but I find it handy to demonstrate how the thing works on the inside, right? So that port D pin 5 means that there's groups of pins around the microcontroller, groups of physical pins, and they're grouped together by the data access that we use them. So we have port A, port B, port C, port E, port D, port E, and I think port F on our pin. And that doesn't mean that there are 150 pins. It is just how they group them and how the memory is laid out and stuff like that, right? So when I talk about a port, it's a group of pins. It's usually port followed by a letter, and then within that port there's a number. So we're looking here at D5. There might be 0, 1, 2, 3, 4, 5, all the way up to 32, but not all of them are exposed. So we only have like 2 bits in port F, and we've got 16 in port A, things like that, right? And that's all defined by how the designers built this thing. And really, it's a lot of lookup and figuring out what's what. So let's look at a little bit of detail here. We could see from this breakout, from this diagram, that port D5, pin D5, is on physical pin 98, and we just count the number of pins all the way around here. So this is the logical software name of the pin, and then the physical pin is pin 98, right? If we look at the logical diagram of what's happening on the inside, is we have a physical pin that's connected through tri-state buffers to a multiplexer. And this multiplexer defines the functionality of the pin. This mux, these particular bits that control the mux, set the functionality. And we can have it set as, by default, the GPIO control, or it could be part of an SPI communications interface, or it could be part of a UART communications interface, or it could have a whole bunch of other functionalities that define, that connect it to a different peripheral. So what the mux bits do is allow us to control what pin is connected to what peripheral inside of the chip. What are we giving control of the pin to? Is it control manually by software through GPIO, or is it control automatically by a timer or a communications interface? So that's what the mux does, right? I'm going to leave it at 0 for now, because setting the mux and then like flipping the bit doesn't actually change the pin. things that we need to do first is enable the clock gating, enable the port itself, or the pin, the port itself, and we do that through the system clock gating registers. And what this does is it basically allows the clock signal to pass through into a particular peripheral. And the GPIO, the interface to the outside world, the general purpose IO peripheral, is a peripheral. So it's a thing we have to turn on. And the reason why we do this is because by not enabling all of the peripherals all the time, we can save a lot of power. And for an embedded system, that's an important thing. So the clock gating bit, we'll talk in more detail about what this means. The clock gating bit enables the port and allows us to control it, right? So that's the very first thing that we have to do is we have to set clock gating. Then we can set our mux to whatever we want. In this case, 0 is the default, and we want Alt1, which is the GPIO, right? Notice that we still don't have control. I can't control it from software yet. So the next thing I have to do is set the pin direction. We're doing GPIO, that's the mux here, and I have to set the direction, which is here. The direction says, is it going to be an input or an output, right? Right now it's set as an input with 0. If I enable it as 1, now it's set as an output. And finally, when I can control the physical pin by writing to this register here, right? Now, you don't have to remember all of the logic here. This is just an illustration to how this thing works and the process for what is sort of interacting and what is going on in all of the registers that we're going to talk about. Okay, so step 1, enable clock gating to the peripheral. So the clock gating, again, controls the power to the port. Each of the peripherals, timers, interfaces to the outside world, GPIO ports, things like that, need to be enabled first. If you don't enable them, you'll get an exception when you try to access their registers. You'll get an exception in the compiler in debug mode. It will throw an exception and pause the program. In running not in debug mode on the microcontroller, you'll get an exception and the processor will drop into an exception handler and hang, and nothing will happen, right? So your program won't run at all. And this will be a runtime exception. Your program will compile just fine, but it'll be a runtime exception and something will go terribly wrong. So the way that we do this is through the SIM, System Integration Module. System Integration Module is basically the thing that enables us to control the behavior of all of the clocks and the peripherals on the system. It's sort of like a core control area. Let's look at that in chapter 12 of the KL46Z processor reference manual. So here's the reference manual. I'm going to use the bookmarks area. I'm in Adobe Acrobat because it's really nice. You can download this or you just use an open source Acrobat reader. And usually they'll have a little bookmarks thing here on the side so I can expand the bookmarks area and it'll give me a list of chapters and that makes it really easy to navigate. I'm looking for chapter 12, which is the system integration module. I'm going to jump down to chapter 12. There's a bunch of stuff in here, but what I am most interested in most of these peripheral chapters, and you'll see the chapters are listed in order, or they're not really listed in any sensible order. They're just all kind of random and weird. But you'll see that each one has a chapter title, and then there's a peripheral name, right? And this is something we're going to see in the code that we need to write too. So it's little hints of where things are and how they're referenced by the names that are given in the code and in the reference manual. So I'm looking at chapter 12, and I almost always want to go to the memory map and register definition section of the chapter. And what this is a list of all of the registers in the system in this particular port and what they mean, right? We're looking for system clock gating control. So I'm going to jump to use the page and index here. I'm going to jump to this part and start looking at these, right? In the notation here, they're doing SIM, System Integration Module, underscore SCGC4. In code, anytime you see an underscore, you should replace it with the member access operator, the pointer access operator, the dash caret or left waka. either one of those. So basically the arrow operator, because these are, the way that they've defined it is the system integration module is sort of a class in the C definition, and then we're accessing the member registers SCGC4, 5, 6, or whatever registers we're going to be using. So when you see this, you can actually use this in code, just do sim arrow SCGC4. Now what we're seeing here is that different peripherals are listed in this register at different locations of different bits for the SCGC4 register, and the bit number is defined on the top, and then the default state of each of the bits is defined on the bottom. So this one looks like it controls communication interfaces, which we're not interested in right now. We'll scroll down a little bit more. This one looks better, so it looks like the LCD, low power timer, and our ports, right? So we're looking for port D. We want to enable port D, and the way we do that is by writing a 1 to this location. This is bit 12, so I want to write a 1 to bit 12 in port, I want to write a 1 to bit 12 in the SIM SCGC5 register. And that will enable port D and allow us to access things on the outside, right? There's a lot of these. They do all kinds of stuff. So most of the thing, anytime we want to access or use a peripheral in the system, we have to first find its clock gating register and bit, and then enable that in our software. So going back to this, the first thing we want to do is find the peripheral we want to use and then enable that bit. For example, to enable port D pins, I have to use the code sim arrow SCGC5, that's the register we just found, and I'm going to put a 1 in bit 12. And notice I'm using the OR operator, so it preserves anything else in the register that already exists. Next thing I want to do is define the pin function. Remember that each physical pin has many functions. So it could be each pin 98, could be something that controls the LCD that's on the board. It could be a general purpose IO. It could be a communication channel. We have to define what we want it to be and what we want it to communicate with and what we want it to be controlled by when we're using it, right? The way we find out what the different settings are is in the reference manual, chapter 10.3, the pinout section. So I'll go to chapter 10, which is signal multiplexing and signal description. So this is how everything is connected to each other inside of the chip. Then we'll go to the pinout chapter, and this gives me a huge table. And what we're looking for, we have a 100 LQFP, and that gives us the pin number, the physical pin number. Remember, we're using 98, so it'll be lower down the line. And also the pin name, so I can look at all the port PTE, PTD, stuff like that. They're not in order, they're just randomly scattered around. So it's really about scanning through and looking for the particular pin that we're looking to work with. In this case, we're looking for PTD5, which is pin 98. And it has a bunch of different functionalities, right? Across here, the default functionality, what it's default set for on reset, what it'll do, and what it's connected to is in this column. Then there's alternate modes for each of the functions that it can do. And there's up to 7 alternates for this thing. So Alt 0 is the default. Alt 1 is typically the GPIO, and that's the one we want. So we need to make sure that the functionality for port D bit 5 is configured to be Alt 1, and that gives us, that lets it be GPIO. When it says PTD5, that means that we're able to control it with software. Other things that it might do is be controlled by the SPI communications interface or the UART communication interface or a timer or part of the LCD control module. To set the functionality, so that's the list of functions. So in the pinout, we saw the list of functions. To actually configure the pin, we have to use the pin control register, which is part of the port module. This is in chapter 11.5, and we're looking for the mux field bits. So remembering that we're using Alt 1, I'm going to, we want to use Alt 1. I'm going to go to chapter 11, And we're going to go again to the memory map and register definition and look at one of the pin control registers. You'll see they're generically defined. And here we've got port X. So the X stands in for the letter of the port. So we're going to be using D. So it would be port D. And then PCRN, which is the number of the bit within the port, the number of the pin within the port that we're going to be controlling. In this case, the hardware package has defined this as this is a class, and then this is an array of registers inside of the pin. And we'll look at an example inside of the port that each register controls a particular pin. And each one of those registers has a bunch of configuration things to do. There's interrupt configuration through ISF and IRQ, and then the MUX pull-ups and pull-downs, all kinds of stuff for configuring how the pin behaves electrically and how it behaves in software. The MUX bits are what we're concerned about, and they have these different functionalities, right? So pin MUX control, alternative 1 is the one we want to set. So we want to make sure there's a 1 in bits 8 through 10 inside of this register. And you'll notice here that the default, what the default is on reset, is undefined. It's dependent on the pins, and we really don't know what it is. So I want to clear these MUX bits first, then I'm going to set them so I know what each one is every single time, right? So the way we do that is there is one register pin per port. In this case, it's port D. If we're going to use a different letter group port, we just replace the letter D with something else. And then we use the arrow operator to get to a PCR register with a particular number, whatever bit we're trying to access. In this case, it's going to be bit 5. So for example, if I want to set port D as port D pin 5 as GPIO, I'm going to access port D pin control register 5. This is index 5, and then I'm going to clear the 3 bits. A 7 is a 111. I'm going to left shift that by 8, which takes me to this region where the MUX is. So I'll have a 111 here, but I'm inverting it and then ANDing it. So this will clear those 3 bits and make sure they're all 0 to start with. And then I'm going to write a 1 into that same area, which makes sure that we are enabled for GPIO. If I want to do a different functionality, I clear those same bits, and then I just set the alternate 3. So from that table, signal multiplexing, nope, pin out, here we go. From that table, if I scroll back down to PDD5, you see there's a bunch of different functionalities. And if I want, each one corresponds to the different alternate function and also the number we have to put in that place, in the MUX place, to do that functionality. So if I want PTD5 to behave as part of a communication channel for the UART protocol, then I would select alternate 3, which means putting a 3 in the MUX position, which is left shifted by 8. Next, we need to set the pin GPIO direction. So each pin can behave as an input or an output. When we talk about input or output, it's from the perspective of the processor. So if I'm the software sitting inside the processor and I'm driving a signal, if I'm turning the pin on and off and it is controlling something outside of the chip, that is an output, right? So an output sends current to a device, an output sends voltage to a device. It is outputting information. We are controlling the pin rather than the pin being controlled. And things that are outputs are things like LEDs and motors. We're controlling them rather than the pin being controlled by them, right? In contrast, we could configure each pin as an input. And as an input, the voltage of the pin is being driven by something on the outside, and we are reading the pin state. So we're reading the voltage, we're collecting current rather than driving the voltage or driving the current. Inputs are things like buttons and sensors, where information is flowing in rather than information flowing out, right? And this is how input and output work in these microcontrollers. Each pin can only be one or the other. It can't be both an input or an output at the same time. It has to be one or the other because there's an actual electrical configuration that happens that we need to set up. And the GPIO pin direction bits do that configuration. We do this through the Port Data Direction Register, or PDDR. This is in Reference Manual Chapter 42.2.6, so let's go look at that. Scroll way down here, Chapter 42, Memory Map and Register Definition, and I want to go to the PDDR, Port Data Direction Register reference. And you'll see here it's GPIO letter and then PDDR. So it'll be GPIO letter, arrow, and then PDDR, and then each of these bits controls individual port pins. So there's 32 bits here. The pin number corresponds to the bit here. So if I'm controlling bit 5, I'll use, if I'm controlling pin 5 of port D, then I'll use bit 5 in this register. Down here, we have a description of what each position means. 0 is configured as general purpose input, and 1 is configured as output. So to set port D5 as output, I will write a 1 to position 5 in GPIO-D arrow PDDR, the data direction register of port D in the GPIO module. Now that we've finally done all these things, we've configured the clock, we've configured the pin functionality, we've configured the pin direction, now we know that we can control it with software. And the last thing we can do is set the GPIO pin state when it's configured as an output. We'll look at how to work with it as an input in a later video. The way that we do this is through the Port Data Output Register, or PDOR. This is in the same chapter 42, and it reflects the current state of the port. And we'll just scroll up a little bit here to get to PDOR. PDOR, here we go. This register configures the logic levels that are driven on each of the general purpose output pins. So same as the PDDR register, each pin within the port is controlled by one bit inside of this register. So we can write a 1 to pin 5, and a logic level 1 will be driven on the pin. That'll bring the pin to high voltage, in this case 3.3 volts. If we write a 0 to position 5, that'll bring bit 5 of port D to 0 or ground. So we can control the state of the pin through software by writing to this register. What that would look like is if we want to set the signal, a high signal on PTD5, we would do GPIO-D, where D is the group of the port. So we were using port D, now we're using GPIO-D. Arrow, PDOR, port data output register, or equals 1 shifted left 5, so that puts a 1 in the bit 5 position of the data output register. If we want to do a 0, then we do GPIO-D, PDOR, and we're going to clear that bit using the and complement of a 1 shifted left 5. Okay, let's review. Let's put it all together, right? For any time we want to set up a GPIO pin as an output, the first thing we have to do is set clock gating for the peripheral. In this case, we're using the port, so we have to set the port clock gating. We'll go and look that up in the SIM chapter in the SCGC registers. Then we have to set the port PCR mux field to GPIO function and read through which ones, which pin and alternate mode we need to set for a GPIO pin. We can find the alternates in the pinout in the system multiplexing chapter. I think that's chapter 10. Then we go to the port chapter, which I think is chapter 11. Then we go to the port chapter and look at the mux field and see what it does and what we need to set it to, and make sure that we set the mux to the functionality that we want to control the particular physical pin. Next, we set the data direction, either as an input or as an output, and then we can set or clear the pin, the logic level, the actual voltage level on the pin through the port data output register as we desire. So what we've done here is we've looked at a lot of different steps for how the microcontroller is configured in order to physically control a pin. And we've been looking a lot at the registers and things like that. We're going to be looking at the reference manual quite a bit. So getting used to the lay of the land for the register manual, for the reference manual, and figuring and determining what these mean is a lot of reading comprehensions, right? So we're going to be reading, and I'm going to be asking you to read a lot of the content in here. I'll be directing you to the general areas, typically the chapters, but it'll be up to you to read through and find information for particular protocols and how it works. Each one of these chapters often has the same things in it. So there's an introduction that's really not terribly helpful. There's an overview that might tell you some of the peripheral features. We don't really know a lot of stuff. We can ignore a lot of the modes of operation. And then we will talk, the useful stuff is the memory map and register definition, which sort of is the map of what each of the bits in a particular peripheral do and how they work. So reading through these, just skimming over what exists and what's there and what looks like it might be useful and what it means will be helpful. But the most valuable part is at the end of the chapter in the functional description, which actually details how the system works and what is working, what needs to be done to do different things inside of the processor. There's no This reference manual is written by engineers for engineers. So there's no like step-by-step do this thing to make this work description, unfortunately, in most of these chapters. So for things like GPIO, we have to piece it together ourselves. For the communication interfaces and protocols, they do give us a little outline, but we still have to figure out what registers to set and what values to set in the registers and things like that. And that means mapping the description of what to do to the registers that we need to set and what values to set them at by looking up these pin descriptions and memory maps and then figuring out what the different fields do and then writing code that sets the field to what we need it to be.